segment is on hypothesis testing. Let's take a look at our steps in the hypothesis testing process. First, we've got to state our hypothesis, our relation that we're going to test. Then we have to select some sort of test statistic. What are we going to calculate in order to perform this test? We need to specify the level of significance. We'll talk more about that. And then state the decision rule for the hypothesis. That is, if the test statistic is greater than this number right here, we're going to reject our null hypothesis. Once we've done that, we collect the sample data, we calculate the statistics, and then we make our decision based on our decision rule and the results of our calculations from the sample. And then we make a decision based on the test results. So a decision about the hypothesis, and then maybe a decision about investment or economic action based on the test results. Now the null hypothesis, we denote that H sub 0, and that's the hypothesis we're going to test. Now, this may seem odd, but that's the one that the researcher wants to reject. And it always includes the equal sign. The alternative hypothesis has to be every other possible outcome. Between the two, they have to cover all possible outcomes. And it's really what the researcher would like to conclude. So say the researcher is looking and thinks that he or she has a strategy for generating positive risk-adjusted returns, a strategy that's going to beat the market. Well, we're going to measure or estimate those risk-adjusted returns, and we would set up our null hypothesis that those risk-adjusted returns are less than or equal to 0. Because if we can reject that in favor of the alternative hypothesis, that's what the researcher would like to conclude or prove, that the risk-adjusted returns on average are greater than 0. So we want to reject the null hypothesis that they're less than or equal to 0. Now, we never really prove anything with hypothesis testing. We're making probabilistic statements. And we don't say we prove the hypothesis. We either reject the null hypothesis or we fail to reject the null hypothesis. So that's the one we're testing. Now, our test statistic is going to be calculated from our sample data, and we're going to compare it to some critical value, and that critical value is going to depend on the significance level of the test. And then if the test statistic exceeds this critical value, or for a test of a point value is outside these range of critical values, then the researcher's going to reject the null hypothesis. So critical values there are like a confidence interval. Our null hypothesis may be that the mean of this value is 0. Well, if we get a value that's too high or too low in relation to 0, then we can reject the null hypothesis that it equals 0. Now in that case, we'd be talking about a two-tailed test. So if we're testing to see if a population parameter is different from a specified value, then we use a two-tailed test. So notice that equal is in the null hypothesis here. The alternative hypothesis is that it's not equal to 0. So we're trying to test whether the mean of this random variable we've got, our test statistic, is equal to 0. Now at the 5% significance level, that means we'll only reject a true null hypothesis 5% of the time. And we do that by putting our critical values here and here. So we have 2.5% in each tail. So now, if we get a value here that's 1 standard deviation from 0, we're not going to reject at the 5% significance level. We've got 1.96 standard deviations here and 1.96 standard deviations below the mean. and that gives us 95% in our interval and puts 2.5% probability in each tail. So the point here is we're going to fail to reject if our test statistic isn't very far from our hypothesized value, and we're going to reject if it's far enough. Well, what's far enough? Well, that's going to be our statistical test. That's going to be based on the distribution of the test statistic. And so what we're really saying here is that if that mean is really 0, we're only going to reject it 5% of the time. And that 5% of the time is called a type 1 error. Now, on a one-tailed test, our null hypothesis has the equal sign, but also a greater than or less than. So let's focus on this first null hypothesis. The mean is less than or equal to 0, versus our alternative hypothesis, the mean is greater than 0. Well, let's draw a 0 here for our reference point. Here we want a significance level of 5%, but since it's a one-tailed test, that puts 5% in our right-hand tail. So our critical value here is 1.645, or rounded to 1.65. Remember, 1.65 was our factor for a 90% confidence interval. Well, a 90% confidence interval put 5% in each tail outside the 90%. So here with a one-tailed test, we're using 1.645 to get 5% in this tail and have a 5% significance level. And that significance level means that we'll only reject this null hypothesis that the mean equals 0 5% of the time when it's actually true. Well, that 5% of the time, that significance level, is our probability of a type 1 error. And a type 1 error, rejecting the null hypothesis when it's actually true. A type 2 error, the other type of error we might make with the hypothesis test, is failing to reject the null hypothesis when it's false. Now, if our probability of a type 2 error is high, that is, when the null hypothesis is false, we fail to reject it a good percentage of the time, then we say the power of our test is low. And we're going to define the power of the test as 1 minus the probability of a type 2 error. Now, we don't have a way in our curriculum here to calculate the probability of a type 2 error. So you just need to know how that relates to the power of a test and what that means. We know that the probability of a type 1 error is our significance level. The probability that we would get a value for our test statistic beyond the critical values even when the null hypothesis is true. Now, our learning outcome statement here, we need to talk about statistically versus economically meaningful results. Well, a statistically significant result is based on our standard error, standard deviation of our test statistic, how far away it is, how many standard deviations we are away. And if we have a lot of data and our test is structured carefully, we can get statistically meaningful results even when these differences are not economically meaningful. So if I estimate the risk-adjusted returns on average for a portfolio strategy, and I have enough data to support it, I may be able to reject the null hypothesis that risk-adjusted returns are less than or equal to 0, even when my test statistic only shows that our risk-adjusted returns from this strategy average 0.1%. Well, that could be a statistically meaningful result, but when you start talking about the transactions costs involved in trying to exploit such a portfolio strategy, or the taxes involved, or the risk in the sense that just because I have a statistically significant positive abnormal return, that doesn't mean I'm going to get that in every period. It may be positive in some periods and negative in other periods, and so there's risk to the strategy of exploiting it too. So it may not be an economically meaningful result, even though it's a statistically meaningful result. Now what do we call a p-value? Well, we can read the definition here. A p-value is the smallest level of significance at which the null can be rejected. The probability of getting the test statistic by chance, even if the null is true. So if the p-value is given as 2.13%, we could reject the null at the 5% significance level. We could reject the null at the 3% significance level, but not at the 1% significance level. Let's just bounce back to an earlier slide so I can illustrate this for you. Let's take a look at our one-tailed test here. Now, we put 5% in the tail here. So as far as our test statistic goes, if we got a test statistic, which is measured in standard deviations from the mean, greater than 1.645, we would reject at the 5% significance level. Well, let's say we got a test statistic that was here. Well, we could reject at the 5% significance level. Our test statistic has exceeded our critical value. Well, what if we had instead of a 5% tail there, a 3% tail there? Well, we're still to the right of that, we would reject. Our 2% critical value might be here. We're still to the right of that. But our 1% critical value might be to the right there. So that's the point. Our p-value of 2.13% says that just leaves 2.13% to the right of our test statistic. So we could reject at a 2.5, a 3, a 5% level, but not at a 1% level. Okay, let's bounce back forward to that and then start talking about constructing a test statistic. Now, if we want to test the mean of a normal population when the population variance is unknown, we need to use a t-statistic. And that means that this statistic is distributed according to a t-distribution. Remember, a t-distribution is defined by its degrees of freedom, which is n minus 1. Now, our t-statistic, our test statistic, is our sample mean minus our hypothesized mean. So this term goes away right here if our hypothesis is that the true mean is 0. Then we're just looking at our sample mean and how many standard errors is it away from 0. So here's our sample standard deviation because we said our variance was unknown. So we have to estimate our sample standard deviation. But if we're testing the mean, remember, the mean is more closely, our sample mean is closer to the true mean, the greater our sample size. So our standard error that we're dividing our sample mean by is sample standard deviation divided by the square root of n, the square root of the sample size. And so our test statistic is really in standard errors from the mean. Standard errors, how many standard errors is it from our hypothesized mean? Now, if we know the variance and we're testing for the mean of a normal population, then we use a z-statistic. Excuse me, that's our standard normal distribution. The difference here is we know the population standard deviation. We're still measuring how far is our sample mean from our hypothesized mean in terms of standard error of the mean or standard deviation of the sample mean around its true value. So let's take an example of a hypothesis test. We want to test the hypothesis that a fund's mean return is equal to 1% per month at the 95% confidence level. Now 95% confidence means 5% significance. Remember, with 95% confidence, we can reject a true null 5% of the time just by chance. So here's the data provided. Our sample mean, 1.5%. So we know that's different from our hypothesized mean. The question becomes, is it statistically significantly different? Or does this just happen by chance because our sample mean is bouncing all over? Well, our sample size here is 45. We have our sample standard deviation of 1.4, and our population distribution is non-normal. So we don't know that we have a normal population distribution, but we have a sample size of 45. So that's a good sample size, and our population standard deviation 1.4%. So with a known population variance and large sample size, we'll use the z-test. I think that's what we had. Yeah, we have the population standard deviation. We don't have to rely on our estimate. That is, we don't have to rely on our sample standard deviation. We know the population standard deviation. So in this case, we can use a z-test. Our hypothesis that we want to reject, and I don't know why we'd want to reject this one. Let's just ignore that for the minute. But we want to reject the null, the researcher does, that the mean is 1% a month, the mean return. So the alternative is just not equal to, so we have a two-tailed test. So what are the critical z-values? Well, for our 95% confidence interval, we're 1.96 standard deviations either side of our hypothesized value. So our decision rule is going to be reject that the mean is equal to 0.1% if our test statistic is outside this range of critical values, either larger than 1.96 standard errors or smaller than minus 1.96 standard errors. So let's calculate our test statistic here. Well, our sample mean was 1.5%. Our hypothesized mean is 1%. So that difference is 0.5%. So now the question becomes, is that a statistically significant difference? Well, what we need is we need the standard error of this mean. So we divide the standard deviation of the population by the square root of the sample size. So that's our standard error. So now we're measuring how far is 0.5% in standard errors. Well, it's 2.396 standard errors above our hypothesized mean of 1%. So we're going to reject our null hypothesis that the mean return is 1% because our z statistic was outside our range of critical values. And pause just for a minute to understand what that means. The difference between our hypothesized mean and our sample mean expressed in standard deviations from the true mean is 2.396. So it's just too big. So statistically, we can reject the null hypothesis that the monthly mean return is 1%. So here's the value we got. That's our test statistic. And we said, well, if this is true, the probability of getting out here, well, that's pretty far. That's getting into the 1% range out there. That might be its p-value. Remember, 1.96 puts how much in this right-hand tail here? Well, 1.96 is a 95% confidence interval. It's 2.5% in each tail. So now we want to look at some other test statistics besides testing the mean of a normal or non-normal population. The other tests you need to be familiar with are the difference in means test. Now you don't need to memorize these formulas. You need to know the application of this. Well, we've got two means from two different populations. So if we have two different populations that we think are normal populations and they are independent samples, one doesn't depend on the other, then we've got a t-test. And that t-test, look what's in the numerator there. It's the difference between the sample means. Clearly, if the sample means are equal, the difference is 0. We're not going to reject this. So just keep it clear in your mind. When are you going to reject this? You're going to reject it when these means are far apart. And all that in the denominator is just to put this in terms of standard errors so we can test it with a t-statistic. If the variance is assumed to be unequal, then we can sum up our sample variances. If we assume that the variances are equal, then we can pool the variances. But, as I say, what you need to know for the purposes of the exam is what a difference in means test is, that the difference in the sample means is in this numerator, and that we're going to reject, that it is a t-test, a t-statistic, and we're going to reject if that test statistic is too large. Now remember, that test was for independent samples. Now we need to talk about dependent samples. So what if we're looking at, we want to say, well, what about the mean returns on ConocoPhillips and Exxon? Are they equal? Well, those are dependent, right? We think that some of the same forces that drive the price of Exxon stock or the returns on Exxon stock also drive the returns on ConocoPhillips, namely prospects for economic growth, current price of oil, etc. So these are dependent. So we can't use the difference in means test. We need to use the mean differences test. And so here we compare them up. We can take monthly returns for the last 60 months for both ConocoPhillips and Exxon and take all those differences. And now we're just going to test whether the average difference is equal to our hypothesized difference. Well, again, if we're saying that they're equal, then our hypothesized difference is 0. So we're just going to test whether the mean of these sample differences is statistically different from 0. And what's in the denominator? Well, our standard deviation of all 60 differences. So that's the individual sample standard deviation. But now we're taking the mean of all 60 differences, so we need to divide by the square root of 60. Because that mean of 60 differences is much less volatile, right? Much closer to the true mean, less sampling error because of our large sample size of 60. So we're going to reject, again, it's a t-statistic, you need to know that, the mean of all the differences, the average difference for our time period is in the numerator, and then we're going to measure that average difference in terms of standard errors. And that's going to be our test statistic. Now, again, let me emphasize, the learning outcome statement only requires you to identify the appropriate test statistic. Those last two are both t-statistics. And interpret the results for a hypothesis test concerning, well, for the difference in means test, we're going to reject if we got too large of a test statistic. It meant the means were very far apart in terms of standard deviations or standard errors. Use that difference in means test when you have two samples and they're normal and they're independent. So they can be different sizes. We want to use that mean differences test when we have two dependent random variables. We need equal size samples. We're also assuming normal population, but there we pair up all the observations, take the average difference, and see if that average difference is statistically significantly different from 0. Now we have a test of the variance. And this is a test of whether the variance of a normal population equals some hypothesized value. So does the variance equal 7? Well, this is a chi-squared test statistic. That's another type of distribution. So our test statistic is distributed according to a chi-square distribution. This is a two-tailed test because we're testing whether the variance equals, for example, 7. So we're going to reject if the variance is statistically significantly less than 7 or significantly greater than 7. So this is a chi-squared test statistic with n minus 1 degrees of freedom. And here's our hypothesized value, and here's our sample variance times n minus 1. And we're going to reject, again, since this is a two-tailed test, a test of whether the variance equals a point value, we're going to reject if we're outside this range of critical values. Now this test here, we're testing for the equality of two variances. So if we have two normal populations and we calculate the sample variance for each, and now we want to test whether those variances are equal. Well, the F-test is a two-tailed test. One side significantly greater than 1, the other significantly less than 1. Those are going to be our critical values. But instead of using an F table with positive and negative critical values, we take the larger sample variance and put it in the numerator. Now clearly, if these two are equal, what does this test statistic equal? Well, if both our sample variances are equal, our test statistic is going to equal 1. And we're surely not going to reject when they're equal. So now, if they're unequal, that could be less than 1 or greater than 1. Well, by putting the larger one in the numerator, we've just kind of rigged the test. We're never going to get a value less than 1. We're never going to be below the lower critical value. So we just have to focus on the upper critical value. Now with your two samples, they don't have to be the same size, so our F-test can have two different degrees of freedom, and that's what you'll see along the borders of it if you look at the table for the F statistic. We've got N1, our first sample, minus 1, that's our 1 degrees of freedom. Our other degrees of freedom measure is 1 less than the size of the second sample. So we are going to reject this if it's greater, if this test statistic is greater than the upper critical value from our F-test. The last thing we have to discuss here in hypothesis testing is parametric versus non-parametric tests. Remember, the parameters of our distribution are the mean, standard deviation, skewness, kurtosis, things like this. Those are our parametric tests. So they're based on some assumptions about how the population is distributed and what the population parameters are. So if we've got a t-test, we're assuming something about the distribution of the test statistic. If we use an F-test, we're assuming that test statistic is distributed according to an F distribution. Now, a non-parametric test makes few, if any, assumptions about the population distribution, and we test things other than parameter values. Excuse me. A runs test is kind of whether things go up or down, right? If a price goes up, each day we'll give it a plus. Each day it goes down, we'll give it a minus. Well, if these changes are random, we can look at the probabilities of getting like 5 positives in a row or 6 negatives in a row. Also, very often use rank correlation tests. A rank correlation test is a test of correlation, but it's based on the rank from one period to the next. We could do this with mutual funds. List 20 mutual funds in order in terms of their performance each quarter, and see if their rank in terms of performance in one quarter is a good predictor of their rank in terms of performance in the next quarter. If it's just random, we might see a zero correlation. If funds that do well in one quarter really tend to do well relative to their peers in the next quarter, then we'd see positive rank correlation. But again, this is based on ranks, not values of returns or anything. So it's a non-parametric test. So that wraps up our segment on hypothesis testing.